Howdy! We are the Precision Sous Vide team sponsored by Professor Kevin Nauka. Our project consists of designing and constructing a sous vide, which is a temperature-controlled water bath which serves as a cooking appliance designed to provide a high-quality cooking experience. This is accomplished by using precise temperature and water level sensors, a heating element, water pumps, and a PID feedback loop that adjusts the temperature of the water so that the food within the vessel cooks at a constant temperature. We're innovating on top of pre-existing sous vides on the market by utilizing a very precise RTD temperature sensor with an accuracy of 0.03 of a degree Celsius and increased water pump flow. This should provide the most optimal and accurate cooking process. Additionally, we're developing an application in conjunction that allows the user to control every aspect of the sous vide through their mobile device.
This is our system block diagram.
My name is Juliana Rosso Acosta. I am a senior electrical engineering major, and I was in charge of the hardware subsystem. This basically encompassed the power delivery to all hardware components, as well as the design of a PCB and assembly of all wiring in a compact electronic enclosure. This allowed for us to use an AC power cable to power the entire appliance, as well as to provide power to all of the smaller components via the PCB interface.
My name is Armando Escalera. I'm a senior electrical engineering major. I was in charge of the microcontroller for this project. This included writing code for all the physical components that were interfacing in the sous vide, as well as writing the PLE server and making sure that we were able to interface with the mobile application and react to those values being sent from the mobile application, as well as sending values to the mobile application. Writing the code also meant testing that everything was working.
I'm Peter Long, and I was responsible for the software subsystem. This included the mobile application, which interfaced with the microcontroller subsystem using Bluetooth Low Energy. The application provides a means for the user to control the entire sous vide system by configuring different cooking settings. Once started, the application guides the user through the entire cooking process and includes timers and estimated cooking times for various different types of food. The application was created on the React Native framework, making it compatible with both iOS and Android operating systems.
Part of our solution hardware was a 1500 watt, 120 volt AC heating element. We chose this as we knew it would give us enough power in order to heat up the water as quick and safely as possible. We also did include a water level sensor, which would help us keep the water level at an optimal state, as we did want to prevent burnout on the heating element, as the heating element does have a constraint as to how much water it must be submerged in.
For the heating element, we needed to design an enclosure that the heating element could be placed in while in the basin so that the user will not be able to touch it. To do this, we designed a cage-like enclosure in SolidWorks and printed it at the FDC using ABS filament, which has a heat resistance of up to 100 degrees Celsius, which matches our engineering specifications. This allowed us to do the final demonstration of our entire system using a real cooking scenario.
So the RTD sensor was a really big part of our project, both budget-wise and functionality-wise, as it was really important to have a really precise RTD sensor that would be able to read the temperature exactly to what the user really wants to cook their food at.
The final hardware component that we used were two mini submersible water pumps. We included these in our design to ensure that there was even heat flow at every point in the basin. We chose 12-volt DC pumps with a pump rate of 900 liters an hour. Using two pumps ensured that the heat produced from the heating element quickly dissipated throughout the basin. These submersible water pumps are also rated to withstand water of up to 80 degrees Celsius, meeting our engineering requirements. For the basin, we elected to use a 27-liter basin because it will fit all of our hardware components, have ample room for the food, and will be able to heat it up quickly.
For the assembly process, we did take an IP68 rated enclosure, put some cable glands in order to be able to pass all of the wires necessary for the hardware components, as well as placing an AC power inlet on the box, which would allow us to be able to turn on and off via a switch. After this, we did add all of the boards, my PCB, the solid state relay for the heating element, the AC to DC chassis, and made sure that all of the wiring was completed and safely put. We also did make sure that all of the wiring was correct, as we did not want any unfortunate events to happen. We did also elevate our electronic enclosure after the assembly was done in order to make sure that no splashes could get on the box and just to keep everything safe. Whenever we first integrated our entire subsystems, and we first made sure that all of the safety hazards were taken into consideration, as we are dealing with AC and water and just electrical components in general. So we wanted to make sure that we had multiple fuses, as well as taking all of the necessary precautions to run these tests as safe as possible. So then we first started by wiring everything the way it's supposed to and powering the entire electronic appliance by simply turning on the switch on the electronic enclosure and making sure that the power delivery was okay, that there was no blowouts, that the fuse didn't blow out, or anything major that could give us concerns. We did move on to segment testing, so we started off with the RTD and the ESP Bluetooth connection. So once we saw the connection was successful, we were able to receive the data needed from the RTD. From then we moved on to the water pumps and turned those on, which was also successful. And then lastly, we included the heating element. So one by one, we sent the signals necessary to the ESP in order to either turn them on and off via the relays that were included in our PCB design. After we realized that our entire system setup was completed and that there were no major issues with the power delivery, we were able to use the same system and setup for the rest of the data collection and system testing that we needed to do.
PID tuning was a really big part of this project because it really added that control element to the Sous Vide system. Having a good PID controller really allowed us to have stability once we reached that set temperature in the Sous Vide. So for this, we first started with proportional control, and just having proportional control on its own was already pretty good at making sure we stay at around our set temperature, but unfortunately there was still some large spikes in temperature. Sometimes the temperature would drop suddenly or increase suddenly, and it would have to make quick corrections to adjust that temperature. And with water, since it was a big water bath, it would take a little bit of time to stabilize again. But then we added the D parameter to the PID, which is the derivative parameter. And once we tuned that, we really got rid of any of those large spikes. It was still a little bit bumpy all around, but it was a lot better than with just proportional control. And then finally adding that integral control really made everything much smoother. And we were able to stay at around our set temperature with no large spikes and no differences bigger than 0.2 degrees Celsius.
After we assembled our full integrated system, we needed to test and validate individual hardware components. Initially, we decided to test and validate our pair of water pumps as they were the safest and easiest. We affixed two thermocouple temperature sensors on opposite sides of the basin. As we were heating the sous vide, we took note of the temperature differences between the two sensors. With no water pumps, we saw that neither temperature sensor read higher values. This indicated that the generated heat was concentrated immediately around the heating element and was not dispersed at all. With a single pump, the temperature of the basin began to heat up somewhat evenly. As you can see on the graph, the temperature sensors read similar values, but there were small discrepancies throughout. Finally, with two pumps, we saw that the entire basin was evenly heated and the two temperature sensors read the exact same value throughout the heating process.
So the RTD sensor, the way that we validated this functionality is we were using a sensor from the materials lab in Zachary, as well as a water bath that they had. We were able to determine our accuracy in Celsius, and it was true that our accuracy proved to be plus or minus 0.02 degrees Celsius, and we were expecting plus or minus 3, but in average we got plus or minus 0.02. So our RTD sensor proved to be effective.
For the power delivery validation, I did check first on the PCB if the power conversion was accurate, as we were going to have 12 volts coming into the board, and we needed 3.3 volts as well as 5 volts. So I took multiple measuring points across the board, making sure that all of the inputs into the various components, such as the ESP and relays, was accurate. As well as for overall power delivery, we were able to see that the power delivery was accurate, as when the switch is turned on, everything powers up and allowed us to have power to the electrical appliance, allowing us to do system testing.
With all systems integrated and validated, we can now focus on usability testing and ensuring the mobile user interface was easy to use. We began running a series of user tests to verify the functionality of the mobile application. After giving the mobile application, which were able to be launched on physical iPhone and Android devices, to two non-technical participants, we gathered their feedback. The respondents noted that there were too many tabs and it was difficult to understand at first. They also wished to see more information about the cooking process. We applied this feedback to our app design, and were able to simplify the tab system, create a more intuitive user interface, and offer more cooking information for the user to see. After making all of the adjustments to the application, we began our final validation test, the one that we've been waiting for since the first day of senior design. It was finally time to cook something with our sous vide system. We elected to do our initial test on a tilapia fillet, as it was cheap, already pre-vacuum sealed, and would be able to be cooked in a short amount of time. As we go through the system operation testing, we will examine the test from the perspectives of the sous vide basin as well as the phone application to get an entire picture of the system at work. Initially, it's important for the application to establish a Bluetooth connection with the sous vide before beginning cooking. The Bluetooth splash page will display a green check indication once this has been accomplished. The user can then verify the current temperature of the sous vide. Next, the user can select the kind of food that they are cooking, how well they would like it cooked, and the size of the food portion. The application will then automatically generate the correct time and temperature that the food should be cooked at. When the user is satisfied, they can click Configure Sous Vide. The system will check to ensure that all cooking requirements are met and that all sensors are functioning. Then the basin will begin heating. An approximate time is displayed on the screen indicating the preheating duration. One of the scenarios we wanted to test was ensuring that the user was notified in the event that there was not enough water in the basin. Without sufficient water, the immersion heating element runs the risk of burning out. For situations which require longer cooking times and or higher temperatures, it's important to consider the evaporation of liquid from the basin, as this could significantly drop the water level of the sous vide. We tested this by removing a pitcher of water from the basin while it was preheating. As expected, the mobile application alerted the user that the water level was too low, and the microcontroller had a check that stopped supplying power to the heating element when it detected that there was not enough water. When the device has reached the optimal cooking temperature, the mobile application will alert the user that the sous vide has finished preheating and the food is ready to be placed in the basin. Once this is done, the user can press the Begin Cooking button on the mobile application, and the timer will count down. The user is able to monitor the temperature and water level of the sous vide, and if any issues arise during cooking, they will be notified. Once the timer has finished cooking, a notification will display for the user to remove the food, and the sous vide will shut down. Comparing it to the original frozen fillet indicates very easily that the food has been cooked thoroughly. Now, it's time to put the finishing touches on this 5-star meal. We'll lightly pan-sear the sides of the fish to simulate Maillard reactions and get a nice golden brown crust. The food is now ready to be served. Are you done yet?
That is good.
Well, that's a wrap.
That's a wrap.
Thank you so much for watching our system demo video. It's been a long journey with many challenges, but we all learned so much along the way. As one chapter of our lives closes, another chapter opens, one with profound lessons and opportunities for growth. So from the entire Chef Facile team, au revoir.